Thank you. And thank you everyone for coming to my talk. Today I'll be discussing fault-tolerant universal quantum processing with neutral atoms. I'm currently a visiting scientist at Caltech. This work was kind of the last project that we did during my PhD, really kind of exploring the fundamentals of error correction with neutral atoms and imagining how it might scale to larger systems. So our work comes along this long path to large-scale quantum computation. And we've seen really incredible progress over the past decade exploring quantum systems with physical qubits, including studying many-body systems and new quantum phenomena. And this has really been enabled by improving state-of-the-art gate error rates in quantum systems down to around 10 to the minus 3 levels per gate. Now, eventually, we would like to scale these systems in order to do large-scale quantum processing and implement, say, cryptographic algorithms or quantum dynamics at scale. Now, these large-scale algorithms are estimated to require up to billions of operations. And as a result, you need error rates on your gate operations of roughly 10 to the minus 10. And so there's quite a large gap between the error rates that we have today and those we need for large-scale computation. And it's currently not believed that one can bridge this gap by just improving devices. In particular, suppressing errors to the required levels that we need for computation is really a central challenge in the field. And the only way that we know to suppress errors to the levels that are required is via quantum error correction. So quantum error correction is so fundamental to the field that before it was discovered, many people were not convinced that quantum computing could become a practical reality. And initially, it wasn't even clear that quantum error correction would be possible. This is because it has to work in a way that's really fundamentally different than classical error correction. In classical error correction, we imagine protecting information via redundancy, such as a repetition code. But this is really a no-go in the quantum setting due to the no-cloning theorem, which states that you can't copy quantum information. And so it was really a theoretical breakthrough in the early 2000s that showed that indeed quantum error correction was possible. And the core fundamental idea was to encode a logical qubit among many physical qubits such that the wave function is delocalized via entanglement. And this delocalization makes it very hard for kind of local physical errors to manipulate the logical qubit and destroy its information. And so then if one wants to detect and correct these local errors, one will measure local operators called stabilizers in order to tell what errors occurred while preserving the encoded information. Now, quantum error correction today is really an extremely exciting scientific and physics frontier. And when we think about scaling up existing devices today, in order to reach this goal of realizing large-scale quantum computation, understanding the best way to correct errors in practice plays a key role in the way that we design quantum architectures. You can't just simply create a system of 1 million qubits and expect it to do a good job correcting errors. It really requires thinking deeply about how one will encode the logical information and do processing on it. And so I think the simplest example that one can use to understand how quantum error correction works is the surface code. So you can think of a surface code as a product of 2 repetition codes. One whose job it is to protect against X errors, the other whose job it is to protect against Z errors. And it exists on a 2-dimensional grid, shown here, of data qubits. And the tiling is the stabilizer operators that we'll use to detect and correct errors. And we'll say that the error-free state is the one with all of the stabilizers, either X-type or Z-type, equal to +1. Now, if a physical qubit error occurs, it will cause stabilizers that it anti-commutes with to flip, enabling us, by measuring the stabilizers and then decoding them using a classical algorithm, to infer which error could have produced our measured syndrome so that we can undo it. Now, the most fundamental theorem in quantum error correction states that as the lattice size, or the code distance, so here it's just given by the vertical dimension of the lattice, increases, we get a so-called threshold behavior, which states that you can exponentially reduce the logical error probability with the code distance as long as your physical error rate is below some threshold error rate. And for the surface code, this threshold hovers at around 1%, which offers us an extremely realistic route to get these very low errors that we need. And indeed, we've seen across several different systems already below threshold behavior, including some of which I'll discuss today for neutral atoms. So it was really the theoretical breakthrough of QEC that allowed the field to take off. And it's understood that eventually we will need to switch to performing algorithms with logical qubits instead of physical qubits in order to reach the deep computation that one needs for these large-scale algorithms. So this kind of gives an idea of the basics of quantum error correction, but in practice, implementing an error-corrected algorithm is challenging. In particular, for large-scale problems, such as factoring, it's anticipated that one will need on the scale of 1 million physical qubits and logical error rates as low as 10 to the minus 10. And furthermore, once we think about systems of this scale, the ability to control a system via classical controls is a major challenge. You can contrast this with how classical computers work, where you have, early computer architectures have on the order of 1 billion bits, and they're controlled with only roughly 1,000 wires to do basic operations like arithmetic and things like that. But many quantum architectures today are wired system where you have several wires per qubit, which, if you can imagine scaling to the millions of qubit range, is quite a formidable challenge to control. So this wire problem poses a significant challenge, but in addition, a major challenge that you reach once you start trying to operate on logical qubits is that because information is delocalized, these logical qubits become very non-trivial to operate on. And it's a really open kind of theoretical question: what is the best way to do processing on these logical qubits? So due to these challenges and the complexity of operating on error-corrected qubits, studies have mainly, and particularly at the beginning of my PhD, had really focused on studying 1 to 2 logical qubits and gates. And the results I will present today will expand beyond this through very careful understanding of the best way to design quantum architectures in order to implement error correction as efficiently as possible. So in particular, the system I'll be focusing on is reconfigurable atom arrays. So this is a schematic of the system that we had in my PhD at Harvard. You have rubidium atoms that are cooled and trapped in 2 dimensions. And each qubit will represent a single, each atom will represent a single qubit degree of freedom in the state of its outermost valence electron. So in particular, we'll store information in the hyperfine ground states of the rubidium atom. And then when we want to generate entanglement, we'll pulse a laser, a Rydberg laser, which is designed to excite one of these 2 states up to a highly excited electronic state, such that the atom will become very large and it'll interact with nearby atoms that are also occupying this Rydberg state. Now, one benefit of this modality is that this is a very stable qubit. So the coherence times for the hyperfine sublevels where we store information are on the time scale of roughly 2 seconds. Now, one really unique opportunity in this system that I want to emphasize, especially in the context of quantum error correction, is that of non-local connectivity. So in particular, using a beam of light, we can pick up a group of atoms and rearrange them in parallel during the computation. By doing this, we can generate gate connectivity between any pair of qubits that we like. So as it turns out, this is extremely useful for quantum error correction, in particular realizing codes with higher encoding rates. But it's also, as we'll see, very beneficial for doing logic gates as well. So here on the right, I show an example of what a circuit looks like with neutral atoms. So here we are realizing a toric code on a torus. The stationary atoms are the data qubits on the toric code, and then the moving atoms are qubits who are measuring the stabilizers of the toric code. So upon doing this, we've prepared the toric code state. Now, as I mentioned, one really nice feature about this system, and in particular, the ability to move atoms, is happens when we try and do computation with logical qubits. So in particular, once you have non-local connectivity, you have the ability to do a very simple type of logic gate called a transversal gate. This realizes a logical gate by simply applying 1 or 2 qubit physical operations on the code block. So for example, suppose I want to entangle 2 logical qubits. I can do a transversal CNOT gate by just interlacing 2 code patches, pulsing on the Rydberg laser in order to do pairwise entangling gates between the 2 codes, and separate them in order to realize a logical operation in just a single step. Now this is very nice from a control perspective because all the physical qubits are doing the same thing. So you only need order of 1 classical controls to basically move this whole group of atoms in order to do a logic gate. In addition, because we can pick up an entire code block in parallel, you can have long-range connections between logical qubits, which is really convenient when we start thinking about implementing algorithms. Finally, this procedure is inherently fault-tolerant. And by that, I mean that because we're doing only pairwise physical gates between the code blocks, you won't spread errors within a code block that could be dangerous and create a logical fault. So this opens up the opportunity to begin exploring fault-tolerant circuits on many logical qubits with low overhead. I'll pause here to see if there are any questions before I dive in. Yeah?
Can fault-tolerant logical gates be realized in ways besides transversal gates?
Absolutely, and we'll actually implement and show a few of those today. Yeah?
So for the inherent fault tolerance, my first reaction to hearing that is like, oh, like maybe to first order, but surely there's some higher order non-idealities here. So I want to ask, sort of, is that analytically true, like completely, that is in fact the case, or are there higher order non-idealities that you might need to think about or compensate for?
It's actually analytically, so we actually, in our work, we prove that if one is doing universal computation with transversal gates and magic state inputs, that the protocol will be fault tolerant in the sense that you will get a threshold theorem and the code distance will be preserved up to kind of a constant factor. And we expect that that constant factor is actually just a shortcoming of our proof technique. We expect that in general, the code distance will be fully preserved, which we've kind of verified numerically. Yeah. All right, I will dive in then. So here I have a picture of a schematic of what the processor looks like. So it's a zoned layout where we have a storage zone where qubits can idle and really be protected by this long coherence time. We have an entangling zone where the Rydberg laser can be pulsed on in order to do gates between pairs or even potentially triples of logical qubits using a CCZ gate. And finally, we have a readout zone where if we move atoms in, we can illuminate them and see which atoms were in 0-1 state. Yes?
So I would guess that this entangling zone has, like, you incur a higher error rate when you're in this entangling zone, right? That's why you have a separate zone for it, right? How long can atoms maintain coherence within the entangling zone? Is there a limit to that?
Great question. So the error rates, the idling error rates are not fundamentally different in the entangling zone. The reason that you don't want to keep qubits in the entangling zone is if they're in the entangling zone and you do a gate, even if they don't have a pair, if they're not intended to do a gate but they're still there, they'll get a little bit of error.
So you have crosstalk, right? Or
I wouldn't call it crosstalk. It's just a local single qubit error. So it's localized to just a single atom, and the error rate's pretty low. In the previous work, it was, I don't know, maybe on the scale of 0.1% per gate.
Oh, so still below threshold. You're
It's
fine.
definitely below threshold, yeah.
Cool.
You just don't want it there not doing gates for too long.
How does that compare with the storage zone?
Storage zone qubits are very safe. So that's where you have like a roughly 2-second coherence time. They're very happy in the storage zone.
Thank you.
Yeah.
Oh, wait, sorry. I meant like what the error rate in the storage zone rather than just like the coherence time. Like, is there any like comparable error rate in the storage zone? Does it depend on what gates you're doing, or is it just like
No.
it doesn't matter? Okay,
It doesn't
cool.
matter.
They're so
just
far away from the
sitting
laser,
there,
it doesn't matter. Okay,
very
cool.
safe.
Cool.
Yeah, very safe.
But you can't do any gates in the storage zone, right? You can't do error correction or anything, right?
Single qubit gates you can,
Oh,
Oh,
but
nice.
not entangling gates. Yeah, so you can do logical. So I mentioned this transversal CNOT, but actually a lot of logical single qubit gates are also transversal. So if you just illuminate a patch, do local single qubit rotations in the storage zone, you can realize a logical single qubit gate. Yeah. Oh gosh. Yes, you.
So why wouldn't you just kind of swap and route inside memory?
Well, we do, but we do it by picking up a whole code block and moving it around.
Yeah, I mean, to do the 2-qubit gates, you could just like not bring them out to some other entanglement zone.
You saying doing like swap gates?
Yeah, like swap the patches to get them to the patch that you want to do the 2-qubit gate to, and not
Yeah.
bring them to this other zone.
So this is much more, much lower error than doing 2-qubit gates. Moving the atoms, they don't really experience any sort of additional noise as long as you've kind of calibrated the moves carefully. So it's actually faster and lower fidelity, or sorry, higher fidelity to just move them. Does that make sense?
No, I was asking, like, instead of bringing the patches to an entanglement zone, why don't you keep them in that storage zone and move them around?
Moved around the logical qubits,
Yeah,
or
just
or
keep them
move
in
the
there.
entangling zone.
Just not use an entangling zone. Like when you want to do the transversal gate between two patches, just move it across and then do the 2-qubit gate there.
That is what we do, but in order to do the 2-qubit gate, you need to be under the Rydberg laser.
Oh, I see. That storage zone doesn't have this.
Yeah, and new techniques actually are exploring moving around this Rydberg
So
laser,
the
which is
laser
really
that does the
convenient.
single qubit gate on the storage zone is different from this.
Yes, it's a different mechanism. This involves the Rydberg state. This is all within the kind of hyperfine manifold.
I see.
Yeah. Yes.
I don't know much about this, but why are the logical qubits and ancilla qubits kind of separated in the storage zone?
Oh, great question. So, yeah, it's very different than a wired system where you have your data qubits and then their nearest neighbors with your ancilla qubits. It actually brings me to my next slide, so maybe I'll just explain it there. Yeah, let me do that, and I think you'll see. Okay, so I guess to outline my talk, in this work we're going to explore kind of what are the key elements that one needs to build a universal fault-tolerant computer with neutral atoms. And so this is an example, this is showing the kind of physical atomic layout of the architecture. We're going to be exploring the various elements and kind of key mechanisms that one needs for fault tolerance and universality, and really understanding their kind of underlying mechanisms in order to reduce the overhead of error correction. So I'll first start by talking about how we can remove entropy from logical qubits and see this below threshold behavior in our system. Then I'll talk about how we can start doing logic gates, focusing on transversal gates. Then I will talk about how one can do arbitrary unitary operations. And I'll end by discussing how deep circuit computation looks in this modality. So let's start with just removing entropy. So first what we're going to do is we're going to take a single surface code. Here you can see the data and the ancilla qubits. It's distance 5. And we're just going to do repeated stabilizer measurements on our surface code. And going back to your question, here we have a storage zone of ancilla qubits, and the entangling zone is where our data qubits will live. And basically, when we want to do a round of stabilizer measurements, we'll take a group of ancilla qubits, drag them into the entangling zone, do in this case, 4 gates required to measure the stabilizers, and then we'll bring the ancilla qubits into the readout zone in order to measure them. And so the reason, to answer your question, that you want your ancilla qubits kind of in the storage zone in their own little region is that Well, each set will be used to measure, in this case, a single round of stabilizers, and you don't want them under the Rydberg laser you don't want the other ones under the Rydberg laser while you're doing that on just a subset. Does that make sense?
Yeah, are they like fundamentally like different from the rest of like the qubits in storage, or?
They're all the same.
Okay, I see.
Yeah.
So
Yes.
what's the difference between the two areas in this, the one that has the more atoms in it?
So the Rydberg laser is up here. This is going to be safe from the Rydberg laser. So when we turn the Rydberg laser on, this qubits in the storage zone won't do any gate. Does that make sense? Yes, so yeah, that's a great observation, yeah. So you can pack them much more densely in the storage zone. The reason that we want them separated in the entangling zone is that this Rydberg interaction is longer range. So in order to not have crosstalk, yeah, you'll want to have them spatially separated by about 10 microns. Yes?
So what the stabilizer measurement means for the neutral atom device? Does this mean taking the photo and look at the image?
You're saying how do we do readout?
Yeah.
Yeah, so I'll actually discuss that in a few slides because we have new methods for atomic readout and this, but in general, the kind of historical way it's been done is exactly as you said with fluorescence imaging. So you'll hit the atoms with a laser, they'll fluoresce if they were in one state or the other. Yes?
So you might have just said this, I might have missed it. So for one block, is there crosstalk between some of the qubits in that block, like nearest neighbors or anything?
No, and we actually carefully benchmark this during this work. As long as they're spatially separated, it's fine. Yeah. All right, I'm gonna keep going.
Wait, I might have one more question. Sorry.
Okay.
Oh, sorry.
No.
I want to keep time in mind. But like, okay, so is the amount of error that you incur in the entangling zone proportional to the amount of time in the entangling zone or the amount of pulses that are done in the entangling zone?
So from gates, the number of pulses, but then there will be some ambient idling noise as well.
They're larger in the entangling zone than in the storage?
It's uniform, generally speaking.
Okay, yeah, cool. Thank you.
Yeah. All right, so the first kind of test that we do in this system with repeated stabilizer measurement is we measure the stabilizers in our system for a given number of rounds. And what we're gonna do is in between rounds, we're gonna inject errors artificially by basically applying single qubit gates with a global angle theta. So here I plot the resulting logical error rate as a function of these injected errors. And what we see is that as you do more and more stabilizer measurement rounds between this injected error, you actually suppress the logical error rate. Furthermore, I'll skip that for a second. So how can we understand this observation here, that as we do more stabilizer measurements, we lower our logical error rate? There's actually two physical mechanisms that lead to this observation. The first is the Zeno effect. So we have this code patch, we've injected an error, a coherent error, but when we go in and we measure our stabilizers, we project ourselves back to a code space. And as a result, this kind of global coherent error will be decohered into individual local errors. And this will be done to order theta squared for each physical qubit. And so this already reduces the errors that we see. Furthermore, when we measure our stabilizers, we gain information about what errors happened. And so we can actually track errors as they occur throughout time and remove the effective entropy that we've injected into the circuit. And so here on the right, you can see the logical error rate as we do more and more QEC rounds. And what we observe is that roughly half the error rate is reduced just from this Zeno effect, which we get by basically looking at the logical error rate, but ignoring the stabilizer information. The other half of the error suppression is due to this entropy removal. So in particular, once we use the stabilizer information, we can then tell information about what errors occurred and remove it by decoding. Yes?
So in a setting where you're not intentionally injecting these kinds of errors, would you believe that this might be actually a little bit representative of what would happen?
Oh, good question. So if we weren't injecting these global errors, then we don't typically see like global over-rotations, and I think that that would reduce the impact of this Zeno effect, and most of the gain that you're getting is from just tracking errors as they occur throughout time. Yeah. Yes? Yes, we do. Actually, I'll discuss that in a slide or two. Yes?
Sorry. I've been trying to understand this point about entropy for some time, but like, so entropy to me means some uncertainty about some quantity, right?
Yeah.
So what does entropy really mean in this context? Like, what is it uncertain about?
I would say that you're uncertain about what physical error actually occurred in your device. Even if you have perfect stabilizer information, you still don't know what physical error generated your observed syndrome, for example. And that's a form of entropy and uncertainty.
But is it the physical error that really matters, or just the logical flips that matter?
Ultimately, it's the logical flips, but if you have a logical error, it's fundamentally due to your uncertainty about what actual error occurred, and that includes what physical errors occurred, at least in my view.
I see.
Yeah. Yes?
So when you say removing the entropy, do you mean detect error, or you mean also make correct?
Great question. So ultimately both. So when we detect errors, we form a belief about what error happened, and that allows us to correct it. That said, one thing I want to emphasize is that you never need to go in and physically correct these errors in hardware. Instead, you can form a belief of what error occurred kind of in post-processing after, or once you've measured your logical qubit, you can form a belief of what error occurred, and then just kind of in your head flip what you think the logical observable should be. Yeah. Yes?
So I think I understood that you said that this is sort of like global 1 qubit error type rotations.
Yes.
Is there, have you sort of quantified the degree to which this kind of procedure performs better or worse for different kinds of error with different structure?
I don't know if we've carefully looked into like which errors are easiest to correct in terms of coherent versus incoherent. I would anticipate that it's similar due to the Zeno effect, which is effectively taking your coherent errors into incoherent errors. Yeah. All right, so now that we've kind of understand the role of repeated quantum error correction, we wanted to benchmark how well it works in practice. So in order to do this, we first need a kind of key addition and experimental upgrade, which is spin to position qubit readout. So this goes back to this question about readout from earlier. In conventional readout, what you do is you have some qubit state, it's in 0 or 1, and then you'll do spin to loss conversion. So you'll basically take one of those qubit states to basically a lost atom. And then you can image whether the atom was present or absent in the trap. This is bad for several reasons that we'll discuss, one of which is that you lose half your atoms when you measure them. One of the qubit states will be completely lost. But the other thing is that it doesn't allow you to tell whether an atom was actually lost before you did the measurement. So what we upgraded the experiment to do was basically lossless state-resolved readout. So this enables us to reuse atoms once they are imaged. And it furthermore allows us to directly detect whether a qubit was lost during the computation. Now, we'll see that this is actually very important for quantum error correction, and it's also a huge fraction of our error budget. So in atomic systems, atom loss is over half the errors. So it's a huge deal, and it's something that we really need to do a good job detecting and correcting. And if you do a good job, as we'll see, you can actually improve performance. So the scheme that was implemented was spin to position conversion. Basically, you have an atom that's in some 0-1 superposition, and will convert whether it was in 0 or 1 to which position it's in, either right or left. And this is done by basically taking a qubit and using a state-selective one-dimensional lattice to basically take one of these two states and transfer the state into the lattice, depending on which qubit state you were in. So then, as a result, we can separate the 0 or 1 states and take a picture. and then know of which state we were in based on if we were on the right or the left side. And if we saw that we were in neither state, then we actually know that the qubit was just not there to begin with. Yes?
Please feel free to not answer this question if you don't want to.
Uh-huh.
But I'd love it if I could hear the details of like how it chooses between 0 and 1. Like, is it a frequency or a wavelength shift that's going on? Like, what kind of physics is letting that happen?
We can, yeah, maybe we'll get into the details more after the talk, but at a high level, one is applying just a state selective potential. Yeah, I'm happy to give more details after. All right, so let's see how we can leverage this new tool once we start doing quantum error correction.
Question.
Yes.
What's the physical separation length between 0 and 1?
Oof, good question. I feel like it's on the scale of roughly a few tens of microns, but I'm actually not sure the number off the top of my head. It's a good question. Yeah, so just to see what this looks like, here we are showing Rabi oscillations between the 0 and 1 state, and then measuring their qubit state with this spin to position conversion. And what you can see is that, just as expected, one will oscillate between the 0 and 1 state over time. And furthermore, this can be done for many, many iterations with just the same atoms due to the non-destructive nature of the measurement.
So can I ask a question about that? So it's hard for me to tell, but it looks like in the intermediate state that you're seeing like 2 dots in the same frame, in the same picture. Is that right?
So this is averaged over kind of many iterations in time. And that's why, yeah, there's, at a certain point in time, they're in a superposition of 0 and 1, so it's just shot noise between those 2 states. Yeah. All right, so let's see how we can use this in repeated quantum error correction. So here again, we're looking at a distance 5 surface code with 4 rounds of stabilizer measurements. And okay, it's a little hard to tell what's going on, but this is kind of an example of a snapshot that we get of the surface codes. And we can directly tell which qubits in the surface codes are lost if they're both absent in the snapshot. So this loss information is actually a huge benefit once one starts to do quantum error correction. So if I have just a Pauli error, I'll see stabilizers flip, but I won't know exactly what error happened. When I have atom loss, I can look at my qubits and pinpoint at a direct qubit and say this was lost. And that's actually much more information that will actually improve the performance of error correction. And the way to handle this is quite simple. What you can do is if you had 2 stabilizers that a lost atom was originally a part of, you can take their product and form what's called a super check, which is just a new stabilizer that now doesn't include the lost atom. So we can still use the information from those stabilizers to detect and correct errors. Yeah?
I'm really sorry, you probably said this, but the fact that it's a data qubit loss and you know it happens means you're getting lost information, not on measurement. Is it like you have like continuous observation and you know immediately when a qubit's lost?
No, that's a great question. And it actually is an important but subtle point. So prior work that's been proposed in the community by people like Jeff Thompson and Shruti Puri has proposed basically checking after every single gate, is this atom lost or not? For many reasons, that doesn't work super well in our system. We much rather prefer to tell if an atom's lost when we just projectively measure it, which you can do in a variety of ways. But as a result, you lose information about when exactly the loss occurred. And so a really important part of when you go and decode is to try and predict when that loss occurred so that you can see, basically after an atom's lost, all subsequent gates are canceled and it'll produce a kind of distinct error pattern. And so it's your decoder's job to kind of predict when the loss occurred so that you can correct those errors. Great question. So in this experiment, we just learned at the end, after our 4 rounds, but in general, there's various ways to put loss detection at periodic intervals in your circuit. So An example is teleportation or measurement-based quantum error correction, where you basically will teleport to a new block. And we'll actually see that in some of the circuits. Yeah. Oh boy. Sorry. Yeah, all right, I'll speed up. But I really like the questions. I would other people understand. Oh, great. Well, maybe I can just keep going and we can ask questions throughout. Okay, so if we use this loss information, we actually reduce the amount of errors that we're uncertain about. And so you can see this here. If we looked at the probability that a detector or comparison between stabilizer measurements is flipped, then if we use super check information, we actually reduce the likelihood that we see detectors flipped because we're accounting for that when we use information about loss. And if you do the most extreme thing, which is post-select on not seeing loss, you have a very low probability that stabilizers are flipped. Yeah?
I'm wondering, when you have to do a super check, do you increase the amount of movement required in order to entangle those 6 atoms with 1 atom, right?
So we're never actually measuring a super check in hardware. We're rather producting the stabilizers once we decode. So,
I see.
Yeah,
okay.
yeah.
Wait, but you've lost. No, you've lost your. Oh no, those are stabilizers, so you can take the product. Okay, cool.
Yeah,
got it.
exactly.
Okay, cool.
All right, running through. So we observe that for this circuit, that we are indeed below threshold, where we can reduce errors by growing the code distance. So you can see that in this plot as we grow the code distance for several different decoders that we looked at. The logical error rate decreases as we go to code distance 5 versus 3. One thing before I explain these decoders that I want to mention is that if you use the loss information, which is these 2 darker lines, you get a drastic improvement in your logical error rate, which is again using this heralded error to do a better job decoding. Furthermore, what we observe is that if you look at shots with less qubit loss, so less heralded errors, indeed you can see that you can suppress logical error rates to roughly 10 to the minus 3 levels. Now, just to mention how we decoded in this setting, we explored 2 decoders. One is a most likely error decoder using integer programming that uses the loss information to predict what's the most likely error that occurred. However, we also explored a machine learning decoder that was trained on our experimental data. And one major takeaway that we had is that ML decoding is actually extremely useful for handling qubit loss. It's this best line here. And it's also extremely fast, so roughly 5 orders of magnitude faster than our algorithmic decoder. So for this ML decoder, we found that we were roughly a factor of 2 below threshold, but I want to note that this threshold is circuit dependent. So here we're just looking at a single logical qubit, but you expect a slight reduction when you start adding in transversal gates, and also once you start going to the very deep circuit limit. And we have, what we then want is, of course, to improve this even further. And I won't go into the details here, but what I want to mention is that we kind of carefully benchmarked our error model, and we don't see any large-scale correlated errors. In fact, most of our error budget is roughly due to experimental bugs that have kind of since been improved from this paper. And actually, results that will come out soon show roughly 3 nines in fidelity with the same system just kind of getting rid of these bugs. Yeah.
So when you say there's no correlated error, this is up to what time scale?
Up to what time scale?
Yeah, like is this, there's no correlated error for whatever long time you run, or like you only verify up to a certain time?
So this is a depth 4 circuit, but we're taking, we took like an order of 1 million shots and never really saw evidence of large-scale correlated errors. All right, I will not get through my entire talk.
I can start counting down from the 10 minutes.
That sounds good. I want to get to how we do logic operations. So before we finish, I don't think we'll get to deep circuit stuff, but that's totally okay. So let me talk a little bit about how we do logic operations. So there are many ways to generate logical gates. 2 main ones are transversal gates that I mentioned earlier, as well as lattice surgery, which is typically done in planar architectures because it just involves interacting codes at their boundaries and doing stabilizer measurements along the boundary to measure logical Pauli products. Now, we wanted to look at both of these types of logic gates and benchmark them. So what we did is we have a circuit where we do many rounds of logic entangling gates between our two qubits, interspersed with quantum error correction rounds in the case of transversal gates. And for lattice surgery, we'll just measure our stabilizers to realize this joint ZZ product. So here I show the resulting logical error rate for these two different types of gates as a function of artificially injected ancilla measurement errors. And one thing that you can really starkly see in this plot is that lattice surgery operations are much more sensitive to errors in your stabilizer measurements. Now, we can understand this because in the transversal setting, our logic gates are realized by directly interacting our data qubits. Whereas in the lattice surgery setting, the logic gate is realized by these ancilla stabilizer measurements. So in the transversal gate, really the only purpose of stabilizer measurements is to kind of track errors and remove entropy. But in the lattice surgery case, the stabilizer measurements are doing the logic itself. And so they're extremely important to get right. And that explains this observation here. And in general, it's known that because you need such robustness against incorrect measurements of your stabilizers, you actually need to repeat this process on the order of d times in order to have sufficient protection against stabilizer measurement errors, where d here is the code distance. So here I show the error per logical operation in the transversal setting as we do more and more C-naughts per round of error correction. So here, we're not even measuring our stabilizers after each gate. We're doing multiple logic gates before we measure our stabilizers. And I'm plotting here the resulting error per logical operation. And what we see is that because stabilizer measurements here are only to remove entropy, actually you can do many logic gates before you even measure your stabilizers. And this is because as long as you're not generating too many errors during a gate, you don't need to just check for errors every time you do a gate.
Sorry, one question.
Yeah.
And I would imagine you only need to check for errors on the qubits on which you've done a bunch of untangling operations on.
Yeah.
Right. So you can. Yeah, that's a huge boon. Okay.
Yeah, it's a big deal, and I'll say this a bit more on the next slide. So we then looked at the error per logic gate as you do more and more C-naughts per round of stabilizer measurement. And here the different lines are just different amounts of kind of soft post-selection so we can understand the physics. And what we find is that the optimal number of C-naughts is roughly 3 per round of error correction, which is actually consistent with theoretical predictions that we'd had from prior to this experiment. Furthermore, we've had kind of continued insights between experiment and theory here that have led us to understand that once you start doing these transversal gates and you start entangling qubits with very little error correction between them, you can get rid of these D rounds of error correction, but to do so, you need to decode logical qubits together. So you need to consider how information and errors passes between logical qubits in this setting. And our recent results have actually shown that this, even though you have to account for these correlations, you can use standard decoders that one would normally use in the memory setting, such as matching for the surface code, even in this setting of logical algorithms. Another big takeaway here is that a logic gate fidelity really is not a single number. It depends on kind of the internal entropy of your code block. So for example, if I'm doing very many C-naughts per round, I have a lot of entropy buildup before I check for errors, and as a result, my logical error rate gets higher. But if I check too often, then I'm not doing a good job. I'm doing unnecessary work, and that also makes things suboptimal. Yeah, back there.
When you say the optimal is like 3 C-naughts per round, from theory predictions, I guess that means you have like opposing factors, right? And what are those factors?
Yeah, it's just what I mentioned. So if you do many gates before you check for errors, you have too much error build up and things get worse. That's on the right side here. If you check too often before errors have built up, then checking itself for errors has a cost because you're doing gates. And so that will also be suboptimal, which is what you see on the left. Yeah?
So would I be correct in thinking that that optimal number might actually scale with, let's say, whatever your physical error rates are? So if those get better, that number will get higher.
Yes. Yeah, absolutely. Yeah.
So is your error correction just measuring stabilizers, or are you doing like a Steen error correction, or have you thought about that at all, or?
Great question. So here we're doing, in this experiment, we're doing kind of just stabilizer-based error correction. What I'll show actually next in the last few minutes is that we will do teleportation-based error correction. Steen error correction is also very nice for these systems. So there's a lot of flexibility. All right, so to conclude, we've found that by leveraging these efficient transversal gates and this correlated decoding, you actually don't need D rounds of syndrome extraction. You only need on the order of 1. And this is actually a big deal when we think about scaling to large-scale algorithms, where you need very large code distances on the order of 20 to 25. It gives us a roughly 25 times speed up for these large-scale algorithms, which is quite substantial. All right, to end, I want to just give you a flavor of how one can take this and do universal computation. So we've looked at transversal gates, but this is actually not enough to do an arbitrary algorithm. And the reason is that if I have a 2D code, like the surface code, only my Clifford gates are transversal. Clifford gates are not enough to do universal computation. You need a non-Clifford or magic gate. And to do this, you have to increase the dimensionality of your code. So to explore this, we'll look at a 2D color code as well as a 3D color code. So what we do is we'll generate this code, measuring our stabilizers, and we'll then apply, again, this kind of global artificial error to our code. So here on the top, I'm showing the kind of logical operator expectation. And on the bottom, I'm showing the stabilizer values between 0 and 1. And what we see is that as we inject errors at a larger and larger angle, we actually have plateaus in our logical information. And these plateaus correspond to transversal gates. So in particular, if you look at this 3D color code, at these angles here, we have a plateau that corresponds to a transversal T gate, or basically a 45-degree rotation about the z-axis, I think. Whereas for the 2D color code, you have no such plateau at these 45-degree angles, and you only have one at a pi/2 angle, which corresponds to a transversal, I believe, S gate in this case. So what we see is that the dimensionality of the code affects what transversal gates you get. Another interesting thing is that we observed is that there's really a direct link between the physical entanglement of the code and your logical magic. So actually, because in the two-dimensional setting for Clifford transversal gates, you actually don't need to prepare your stabilizers to be +1 in order to execute this transversal Clifford gate correctly. And this is because if your stabilizer is -1, you can track its propagation deterministically through the gate. On the other hand, if I am trying to do a transversal non-Clifford gate and I have the wrong stabilizer signs here in the gray, then we see that we completely lose our transversal gate, and actually the performance and the behavior is identical to if you just had physical qubits. So here it's very important to create this entangled state in order to get our transversal gate. Yeah?
I have a question about this. Like, this statement about physical entanglement being necessary for logical magic, is this a statement only for the 3D color code, or do you think it's a general statement for all
It's a general statement.
For like literally all codes?
Yes, for codes with transversal non-Clifford gates. In order to do the gate correctly, you have to prepare this very special entangled state to get the desired logical action.
So both of the X and Z stabilizers, they both need to be +1, or one of them can be -1?
Oh, great question. one basis can be -1, and I believe that's the z basis. And the other basis will propagate deterministically through. Or the z basis will propagate deterministically through, the x basis will not. Okay, so just to wrap up, I hope I've given you a flavor of what quantum error correction can look like with neutral atoms. I think that there's a really exciting frontier ahead for quantum error correction, both in neutral atom systems where there's a clear pathway to scaling to tens of thousands of qubits, and additional abilities to do continuous reloading in order to access deeper and deeper computation. There's also been a lot of recent incredible progress across the field in superconducting qubits and trapped ions. And I think it's a very exciting time. It's clear that quantum error correction works, and there's been a really remarkable exchange of ideas within the field. So with that, I want to finish by thanking my collaborators. So this is the Atom Ray team at Harvard. I'd also like to thank my PI, Misha, as well as Vladan and Marcus, and the large team of theory collaborators as well that helped make this work possible. Thank you.